Hi everyone! Today we're going to be looking at extremas, changes, and bounds of functions. Here's today's FLT. Given a function, I will be able to identify local extremas, changes in intervals, and bounds. First, let's take a look at the local extremas of functions. So let's break down this word, local extrema. So what does this mean? Well, extrema is just like a fancy way of saying maximum or minimum points. And then local is just nearby or like in the area. So the local extrema is just the maximum points or minimum points in the local region you're looking at. So for example, let's say we have the graph of this function, and try your best to sketch this out in your notebook. It doesn't have to be exact, but try to make it as similar as possible. If we focus on the local area around the point A, notice that A is the highest point there. So A is a local maximum. And then if we focus on the local area surrounding point B, notice that B is the lowest point in that area, so that's why point B would be a local minimum. But what about point C? Notice how for point C, no matter how much we zoom in, so no matter how local we get, there's always some point that's a little bit higher than C, and that's also a little bit lower than C. So point C is neither a local maximum nor a local minimum. So in this case, point A and point B are local extremas. Again, they're your local high points or your low points. So let's take a look at different kinds of functions. So let's first focus on linear functions. So let me just sketch out a line. And then you can choose any point on this line. Let's see, I'll choose here. Notice how linear functions, there is no local extrema, because no matter what point you choose, there's always a point that's slightly higher than it or slightly lower than it, so there's no local maximum or minimum. What about quadratic functions? So what about parabolas? So let me sketch one like this here. Notice at this point, there is a local minimum. And then also, what if I sketch a parabola that's reflected? In this case, we have a local maximum, the high point. So for quadratic functions, we can have local extremas. So let's take a look at some examples together. So for our first example, find all local extremas of the function y equals x to the fourth power plus 3x cubed minus 4x plus 5. Don't worry, you're not expected to sketch this. You can just graph it on Desmos like I did. And then I have a few points that I want to focus on. First, let's look for any local maximum points. Notice this point right here. This seems to be a local maximum. And this seems like the only local maximum. So I have one local maximum. at, let's see, negative 0.843, comma 7.08. So we have a high point here. And then what about local minima? Do we see any local minima in this function? We actually have two local minima for this function, one right here and another one right here. So I have two local minima. That's the plural for minimum. So I have two local minima at negative 2, 5, and also 0.593, 3.377. So for this example, I have 3 local extremas in total. Let's look at another example together. So find all local extremas of the function y equals negative 2x to the 4th power plus 4x cubed minus 2x plus 3. And then your graph vaguely resembles the McDonald's logo. Wow. So here, how many local maxima are there and how many local minima are there? Let's take a look. So notice for this graph, we have 2 local maxima at these points. So let's write it out. We have 2 local maxima at, so the first one is at negative 0.366, comma 3.5, and also at 1.366, comma 3.5. And then we only have one local minimum for this graph right here at this point. So we have one local minimum at the point 0.5, comma 2.375. So here we had 3 local extremas again, but for this one we had 2 local maxima and 1 local minimum. So on Edpuzzle, please find all local extremas of the function y equals x cubed minus 8x squared plus 19x minus 11. The graph is already provided for you. Please find all local maxima and all local minima. Next, let's look at changes in intervals. So here we're just looking at how the graph changes. So a graph can be one of 3 types. It can either be increasing, so going up, or decreasing, going down, or staying constant, so a horizontal line. And for changes in intervals, we only focus on the x values. Also, as you saw in the graphs earlier, a function might not necessarily be increasing the whole time or decreasing the whole time. That's why we take a look at the changes in intervals to see how the function changes over time. Like at first it might be increasing up to a certain point and then start decreasing. So for our first example, let's identify the change in intervals of this function. Y equals the absolute value of x plus 5 plus the absolute value of x minus 3. Again, you're not expected to know how to sketch this, so you can graph it on Desmos like I did and get the following graph. So what do you notice about this graph? When is it decreasing? When is it increasing? And at what interval is the graph staying constant? Let's write it out piece by piece. So we look at a function going from left to right as if we were reading a book. So notice that we first decrease. So at first the function is decreasing. Decreasing from where? Well, it's decreasing from the leftmost start point, which is negative infinity. So when the function goes all the way to the left, it's just going all the way to negative infinity, all the way up to negative 5. And again, we're just looking at the x values for this part. So from negative infinity to negative 5, the function is decreasing. And when we're talking about changes, your interval is always open, so we use the parentheses. Let's continue following our function. Right here, it's just a horizontal line, so we're staying constant up until when x equals 3. So from negative 5 to positive 3, the function is constant. It's a horizontal line. And then lastly, the graph increases from 3 all the way to positive infinity. So from 3 to infinity, the function is increasing. So this tells you how the function changes over time. From negative infinity up to negative 5, this function is decreasing. But then it becomes constant up to 3, and then after that, all the way to infinity, this function continues to increase. Okay, for this next example, we're going to identify the change in intervals of this function, y equals x squared over x squared minus 1. Notice this graph looks a little different compared to the graphs we've been looking at before, but I included some dotted lines so that you can see how the function approaches a certain point but doesn't exactly touch it per se. So from negative infinity all the way to negative 1, so right here, we are increasing. This function is increasing up until a little before negative 1. We don't exactly hit it. And then starting from right after negative 1, we're increasing again, right here. So we write it as a separate interval, but the graph is still increasing from negative 1 to the origin, 0. But what happens after? We start decreasing. So the function starts decreasing from 0 to 1. So right here, the function is decreasing. Again, this goes almost up to positive 1, and then we resume right after positive 1. The function is still decreasing, and it continues decreasing all the way to positive infinity. So in this case, our function increases from negative infinity to negative 1, takes a little break, resumes right after -1, continues to increase until 0, and then starts decreasing until 1, takes a little break at 1, resumes right after 1, and continues decreasing all the way to positive infinity. On Edpuzzle, please identify the change in intervals of the function y equals the absolute value of x plus 4. Try sketching this on your own and then graphing it on Desmos to make sure. How does the function increase or decrease or stay constant? Our last topic for today is boundedness. This is a really fun word to say, boundedness. So the bounds of a function tell you how far you can go. Think of a basketball court, which has its bounds, and you can't go out of bounds, right? So same thing with a function, you want to stay inside the bounds of a function. Let's take a look at the boundedness of linear functions. So again, I'm just going to do a quick sketch of a linear function. So just drawing a line right here with technically the 2 arrows on the end. And these 2 arrows signify that your function goes on forever. So this linear function, or actually any linear function, is not bounded because it could go up and up forever or go down forever. But what about quadratic functions? What is the boundedness of quadratic functions? Do you think quadratic functions have any upper or lower bounds? So let me sketch a parabola really quickly with these arrows. So here, notice that this parabola will keep going up forever and ever, but it does have a lower bound at this point, which is also called the vertex, by the way. So this function is bounded below, because you can't go any lower than that point. And then what if we have that reflected parabola? So this function can go down and down for a really long time, forever basically, but it can't go past this point up here. So it's bounded above. So this top parabola is bounded below, and this one is bounded above. So as you saw, there's a few types of boundedness. A function can be not bounded, like the linear function we saw, or bounded below, or bounded above. It can also be bounded by domain, which kind of looks like this, but we won't touch on that today. So let's look at some examples. For this one, let's identify the bounds of y equals -3 times x minus 4 quantity squared plus 7. Technically, you guys do know how to sketch this function, but I decided to just go ahead and graph it on Desmos. So we're going to focus on if there are any upper bounds, so like a roof, or if there are any lower bounds, like the floor, the floor, for this function. So this function is going to keep going down forever and ever. I'm drawing in the arrows. It's going to keep going down forever. But it can only go up to a certain point, this point. So this graph, this function will not go past the line y equals 7. So this function is bounded above. And tying it into our previous topic, the range of this function is from negative infinity to positive 7. 7 is the upper bound for this function, so there's a connection between boundedness and range. So let's do one more example together. We're going to identify the bounds of the function y equals 2 times the absolute value of x plus 3 minus 4. This one too, even if you didn't have Desmos or a graphing calculator, you can probably sketch it out. But anyway, here's the graph. Do you notice any lower or upper bounds for this function? Well, this function keeps going up and up forever, all the way to positive infinity, so there's no upper bound. But there's a low point. We can't go below the line y equals negative 4. So in this case, this function is bounded below. So this line right here is my lower bound. Anything lower than that is out of bounds. And let me also write the range. We go from negative 4 all the way to positive infinity. Again, there's a connection between boundedness and your range. On Edpuzzle, please identify the bound of this function, y equals 0.3x squared. Is there a lower bound or an upper bound, or are there no bounds? So today we looked at 3 things, and the first thing we looked at was the local extrema. So your local extremas are the highest, so the maximum, and or lowest, minimum, points in a local region of your graph. So when you look at a graph, identify the local high points or low points. And then the second thing we looked at was our change in intervals. So the changes in intervals tell you where the function increases, decreases, or stays constant. So it tells you how the function changes over time, like how it could be increasing for a while and then stay constant, or decreasing for a while and then start increasing at a certain point. The changes in intervals tell you how the function changes over time. And then the third topic we looked at was the boundedness. So the bounds simply tell you how far you can go on the function. And it has a very similar idea with the range. Please remember to submit your notes on Canvas, and see you guys next time.